Hi friends, welcome to gmk tutorials. ఇప్పటివరకు ఇంకా ఎవరైనా మన ఛానల్ సబ్స్క్రైబ్ చేసుకోకుండా ఉంటే సో ప్లీజ్ సబ్స్క్రైబ్ అవర్ ఛానల్ ఫర్ లేటెస్ట్ వీడియోస్. Okay, so today we are going to discussing about a small signal analysis. So before starting of this small signal analysis, first of all you have to know about some basic topics related to the diode. Okay, then later on we will move on to the small signal analysis. Okay, so generally PN junction diode is nothing but the symbolic representation is nothing but this is generally called as a diode. Okay, so it is anode, it is nothing but a cathode. Suppose it can be represented as a D, so where D is nothing but a diode. So D is on, that means diode is in on condition, means that it acts as a short circuit. When it is on condition, when it is on, the diode is in on condition or diode is in forward bias condition, whenever, okay, whenever this potential, I will call this potential as a VA, so this potential can be treated as a VK. Suppose the potential VA is greater than VK, that means anode voltage is greater than cathode voltage, then only the diode is in D is in on condition. Okay, it is also called as a short circuit condition. Okay, we can also call it a short circuit. So this is generally, suppose if you are taking diode is in a ideal case, suppose if you are taking diode is a practical case, the anode voltage VA is greater than cathode voltage plus V gamma, where V gamma is nothing but cut-in voltage of the PN junction diode. So cut-in voltage of the PN. So this is for practical case. If you are taking diode in a practical case, so this is valid for ideal diode. Okay, this is valid for ideal diode. That is the case. Okay, suppose if you are taking diode is in, suppose if you are taking diode VD is equal, diode voltage VD is equal to, diode voltage VD is equal to VA minus VK, diode voltage VD is equal to VA minus VK. That is nothing but the potential difference between anode voltage and cathode voltage that gives the diode voltage. Practically this diode voltage is 0.3 or maybe 0.7. For 0.7 for silicon diode, 0.3 for germanium diode. Okay, 0.3 for germanium diode and 0.7 for silicon diode. As well as the VI characteristics of diode, if you are observe the VI characteristics of a diode, suppose if you are taking a VI characteristics of a diode, VI characteristics of a diode, let it be, draw this one. Okay, so this behaves like a, this is a characteristics of a VI characteristics of the diode. So it represents a current I, it represents a voltage. So here over a certain voltage, after certain voltage, whenever the corresponding PN junction diode, whether it may be silicon or germanium, suppose if you are taking one more diode like this, so this is a case for silicon diode, this is a case for germanium diode. So the germanium diode is going to be on condition at 0.3 only. So it may be started, suppose if you are taking very close of curve, this one, like just okay, if you draw the curve for this one, it may be started like this. Okay, so at around 0.7 onwards it starts the conductor. But if you go for the practical point of view, If you go for a laboratory point of view, for in case of the electronic devices and circuits lab, or maybe any electronics labs point of view, the cut-in voltage around starts with 0.45 onwards. The diode is going to be on condition. Okay, the diode is in on condition. Okay, that is a practical case. So one more important point I have to note here is the slope represents the resistive behavior. Whatever the slope is there, so the slope represents the resistive behavior. The slope represents the resistive behavior. Slope represents the resistive behavior. Slope represents the resistive behavior. Suppose if you are taking in case of the Ohm's law, as per Ohm's law, what is the condition for Ohm's law? V is equal to IR. Suppose if you are taking a resistor R at that time, so this is a current passing through the corresponding resistor. If the current is increases, obviously voltage drop across this resistor is also increases. That means it is linearly increasing, right? As the voltage increases, the current increases. That means it maintains some kind of a linearity, right? It maintains like this. So this is a resistor behaves as a linear element also, right? Coming to the previous slide, right? We will take one more blank. Okay, this is the case for if suppose if the diode is in on condition, if the PN junction diode is in on condition, the current equation ID is equal to I naught into e power Vd by eta Vt. So this is a diode equation. Suppose if the diode is in on condition. Okay, so the graph of this diode is like this. So this is the VI characteristics for a diode, or maybe IV characteristics or current voltage characteristics of a diode. This is nothing but Vd, this is nothing but ID for notational pointer. Suppose if you are taking like this. So this is the voltage. So this curve is same for irrespective of the circuit. Okay, whatever the circuit, the P injection diode behavior is like this only. Suppose if the diode is connected in a circuit, okay, if a diode is connected in a circuit, let us see what is the variation. Suppose I will take one diode, one circuit with positive, so some supply voltage plus or minus V. So this is nothing but a diode connected in series point of view, right? So this is a resistor R, this is the P injection diode. At the same time, let it be I can call this a current called ID. Okay, the voltage drop across this one is equal to Vd. So that means it is nothing but some voltage, this is nothing but some resistance. So here the scenario is completely different, right? Suppose the voltage V is fixed voltage. Okay, if the voltage is V is fixed, R is also some fixed resistance. This R is also called as a biasing element. This R is also called as a biasing element. Suppose if V is applied to this one, suppose if your voltage V is applied to the corresponding circuit, the diode is in on condition, okay, it acts as a short circuit, therefore some current is passing through the diode, as well as the diode current is also passing through the resistor, which produces some voltage drop that can call as a Vd, right? That is very clear, right? So instead of that one, just I have to apply the KVL in this circuit. As per KVL, what is the equation here? As per KVL, the equation for this one, the supply voltage V is equal to VD diode voltage plus diode voltage, current passing through the corresponding into resistor R. So this is a diode equation. From this equation, if you write the diode current equation, ID is equal to what is the value? That is nothing but minus 1 by R into VD plus V by R. This is the equation. This is the equation for diode current. This is the equation for diode current if a diode is connected in a circuit. So this is the equation for diode current when the PN junction diode is in on condition. So both are different, right? It is an exponentially representation. This represents a y is equal. Suppose if you are comparing this equation with the standard equations, y is equal to mx plus c. So that represents, where m represents the slope of this one, this constant represents this one. That means the diode equation is similar to the straight line equation if the diode is connected in some circuit or maybe some closed circuit. Okay, some closed circuit. This diode equation is also called as characteristic equation. Okay, the diode equation is also called as a characteristic equation. At the same time, let us see some more notations for this one. Suppose the diode equation ID is equal to minus VD by R. Okay, 1 into, so I will write it. So 1 by R into VD plus V by R. So this is a diode equation. This is a diode equation, or we can also call it a characteristic equation of a diode. Characteristic equation of a diode. Okay. So if you are comparing this equation with the standard slope equation, y is equal to mx plus c. That means the diode equation or the diode represents a straight line in the case of a closed circuit point of view. So from this, where slope m is equal to minus 1 by R. So m is equal to minus 1 R means that the equation for this one is equal to like this. So this line represents the slope of minus 1 by R. So this is generally called as a ID. This is generally called as a VD. Okay, this represents a slope of minus 1 by R. So this straight line with a negative slope. So that means this represents this straight line with a negative slope. That means the diode current exhibits a straight line with a negative slope of minus 1 by R in case if you are connected a diode in a closed circuit. That is very important. Right? So the highest voltage that can be experienced by the diode is generally called as the highest voltage that can be experienced by the diode is generally called as a supply voltage. Okay. At the same time, the highest voltage experienced by a transistor that is generally called as VCC or maybe VDD. Suppose if you go for an operational amplifier, the highest voltage that can be experienced by that device is generally called a plus VSAT or minus VSAT. Okay, those are the some voltages point of view, right? So let us move on to the very important conclusion. So here, suppose, just we will take this color, right? So previously we know that the diode equation current is, when the PN junction diode is in on condition, this is a current I, this is the voltage V. So the graph of this one is equal to like that. So PN junction diode basic graph is like this. It is in when the diode is in on condition. This is important, when the diode is in on condition. At the same time, from this analysis, you will have a one clarity, that is nothing but when the diode is D in circuit, when the diode is in a circuit, connected in a circuit, this is the graph, this is the characteristics of this one. Therefore, if you draw the plot of for this one, just you will get like this, right? So this is the case for diode is in closed circuit. Diode is in a circuit condition. So whatever the point, that means the two graphs meet at a some point, right? Meet at a some point. That point is this, right? This point is generally called as a quiescent point. Okay, this point is also called as a quiescent point, or we can also call as a Q point. Okay, quiescent point we can also call as a Q point. At this point, the diode is in operated in the circuit because of V and R is fixed. That's why this point is called as this fixed point is called quiescent point. In this consideration, both voltage and R values, V and R values are fixed in the corresponding circuit. So that's why this point is generally called a quiescent point or operating point of the PN junction diode. Operating point of the PN junction diode. Okay, operating point of the PN junction diode. Suppose if we want to get the Q point in the external biasing elements are needed, so DC biasing voltage is also needed. Suppose if you want to get the Q point, suppose if you want to get the Q point, so this point is generally called a Q point. If you want to find out the Q point for this one, in this case you need two things, that is nothing but external biasing elements, at the same time some fixed voltage. So if you have these two values, you can get the quiescent point. This quiescent value also refers to the value of a current or voltage in a transistor in the absence of AC input. So this quiescent point is also called as a quiescent point, also refers to the absence of AC voltage. Quiescent point is also called as absence of AC voltage or current. Okay, so quiescent point is nothing but absence of AC. That is also one of the important point of view. Okay, so this line is also called as a DC load line. Okay, this line is also called as a DC load line. This line is also called as a DC load line. This line is also called as a DC load line. Suppose if we take the piecewise linear characteristics point of view, piecewise linear characteristics point of view, this is a DC load line. If you draw the tangent, to this point, if you draw the tangent, just a wait. If you draw the tangent to this line, you will get like this. So this black color line represents the tangent of this one. Okay, if you draw the curve like this, this is a final graph representation for that one, right? So let us see here. So this is a similar to like this. So this line represents some slope. This change in the mode, it represents a slope. Okay, so one important point is nothing but in case of the DC load line point of view, from 0 point some current, some 0 milliamps, so 0.1 milliamps to 10 milliamps range. So 0.1 milliamps to 10 milliamps range, 0.2 to 10 milliamps range. Whatever the current you have in case of the normal diode or actual diode, as well as tangent current is also only difference of 50 milliamps only. That's why both cases the current is also same. That is also one important point for this one. So from this point of view, suppose if you want to represent the diode in case of the equivalent point of view, that is generally equal to, this is a final one. Okay, the diode with some cut-in voltage V gamma, some resistance. This is the equivalent circuit for the p-n junction diode. This diode voltage 0.7 volt is plus or minus. Okay, so this is having some resistance of R. That is the equivalent circuit for a p-n junction diode. Suppose if you are applying some small signal to this one, suppose if you are applying a small signal for this one diode, small signal. Suppose if you are applying a small signal, this small signal is nothing but a signal variation is much smaller than the quiescent or DC value, then such amplifier is called the small signal amplifier. Okay, so small signal amplifier. So for this purpose, let us see here some general consideration. It is having some signal like this. Suppose if the signal is having a 5 volts peak to peak, obviously the p-n junction diode is in on condition. It produces some kind of the waveform that it allows only positive half cycle. For the during the negative half cycle, it acts as an open circuit. Suppose if the voltage is very less than that of the cathode voltage Vk, obviously D is in half, or it may be in reverse bias condition. The diode is in reverse bias condition. Moreover, if you are applying a directly voltage if you are applying a small signal to the p-n junction diode, it does not allow the signal, because of whenever the diode is operating in the quiescent point or operating condition only, then only it behaves as a resistive nature. Whenever the device behaves as a resistive nature, then only it passes the small signal through the corresponding circuit without any degradation. That is also very important. So for that purpose, in order to maintain a same relation, in order to maintain a same thing, first of all you have to set the corresponding p-n junction diode in DC bias, and later on you have to apply the AC voltage. Suppose, so that is nothing but, so first of all you have to make this p-n junction diode in a quiescent point or operating condition. Suppose you have to first keep the p-n junction diode in a Q point region or operating region. So for that purpose, first of all you have to apply some positive voltage, later you have to apply some small signal. Okay, then only the PN junction diode allows the corresponding small signal. Okay, small signal. So the graphical representation or characteristics of this PN junction diode, I V characteristics, it is like this. So it behaves like a piecewise linear format. At the same time, if you draw the load line for this one, you will get a Q point. Okay, this Q point, this is a Q point, right? This represents a Q point. So this is a signal representation. So whenever the Q, this is generally called a Q point, Q send point, also Q point. Q point is also referred as Q options of AC. Options of AC. Therefore, if you are behaving like this, obviously, if you have a diode voltage, diode current, and diode voltage, you can find out the slope of this one. So the graph or maybe characteristics represents a linear nature. This represents a resistive behavior. When the resistive behavior means that obviously it allows the current in a linearly. That's why in case of when the PN junction diodes behaves as a straight line behavior or maybe linear behavior, at that time it allows the small signal to the corresponding circuit. But if you want to make the PN junction diode in a linear behavior, first of all you have to set the corresponding diode is in quiescent point. Okay, then only you will get the corresponding analysis, right? So at the same time, if you calculate the slope of this one, that is nothing but R is equal to slope of this one. That means if you want to calculate the dynamic resistance, RD is equal to 1 by slope. So slope is nothing but obviously variation of the current related to the, so that is also equal to slope. S is equal to ID by VD, change in current by change in voltage. Therefore RAC is equal to 1 by slope. Okay, 1 by slope. Therefore you will get final value. Just I have to represent final value. So G is equal to R, so RAC is equal to 1 by GAC, that is equal to eta VT by IDQ. Okay, this is the slope equation for this case. If you want to find out this derivation, first of all you have to draw the current equation. ID is equal to I naught into e power V by eta VT. Okay, then you have to perform the derivation with respect to VD. You will get the equation like this. So this is all about the behavior of the PN junction diode in a closed circuit as well as in a normal on condition. So thank you for watching GMK tutorial. So the password for this PDF is PN junction. Okay, the password is PN junction. Password is PN junction. This is a password for this PDF. Okay, thank you guys. So capital PN, J is also capital junction. Okay, thank you for watching GMK tutorial. Thank you.